Today I'm going to talk a little bit about something I developed in collaboration with François Baccelli, who is in France also, which we called Replica-mean-field limits. And I decided to introduce this framework that we developed, the computational framework, in relation to metastable dynamics in neural networks. Okay, so that's the theme that I will follow sort of to introduce this framework. But before I get into more details, I just want to make a little forward. So as mentioned by David, I'm in between two departments. So I do math and neuroscience. And I just want to be clear that when I apply math to a system as complicated as the brain, I'm somewhat humble. I don't claim that we are going to get the same success that we get with inanimate system. And what I'm really after is trying to use neuroscience problem as a source of inspiration for possibly innovative new mathematical technique, and also hopefully along the way get some new biological insight about a question that is of interest to the neuroscience community. Okay, so the broad context I chose to introduce replica-mean-field limits are going to have to do with metastable dynamics. So why should we care about metastable dynamics? So perhaps a good way to introduce them is to consider the problem of modeling memory retrieval in the brain, and specifically in the hippocampus. So we've known for a long time that the hippocampus presumably has something to do with memory. And if we're interested in maybe understanding or modeling how memory may be encoded, well, we have to make a model. And so people have observed that in a certain region of the hippocampus, CS3, there are networks of neurons, and those neurons exhibit a very high degree of recurrence. And this idea motivated people to say okay, maybe the business of these neurons that are involved in highly recurrent networks is to actually form a high-dimensional energy landscape. So it's an effective representation. And those high-dimensional energy landscape encode memories as minima. And basically, when you are trying to retrieve memories, you can model it or think of it as a biased random walk in this complex energy landscape, where basically when you have a memory in your mind, you're basically hovering around a local minima. And your experience or other external input may bias this walk and then transition you to another local minima, another memory. And so that suggests that this process of memory retrieval can be modeled as a metastable dynamic. And metastable dynamics here means that if you think about what's happening on the short time scale, you're just hovering around a state that looks like stable, so it's a quasi-equilibrium. But if you look at it on a longer time scale, then the dynamic will be dominated by sharp transition between those quasi-equilibria, because presumably there are more than one, okay? So it may be of interest to be able to have a clear understanding of how those metastable dynamics may arise. And before I tell you what I think understanding those dynamics means, a first question may be, okay, how hard it is to make a model that will exhibit such behavior, and a model that will be more network-based model rather than an effective energy landscape-based model. And so the answer is that it's not too hard. So here, a picture that is taken from a publication by the Mazzacuto lab that specializes in metastable dynamics. And in that picture, they just evidence what is the difference between a stable network, so the one to the left, and a metastable one. And those pictures are obtained by simulated spiking networks. And so the first stable one is just a randomly connected homogeneous network of spiking neuron with intrinsic noise. And because there's no structure to that network, the dynamic is fairly stereotypical, and all it does is relax to a typical state and just stay in that state. So it's stable, okay? Now, if you want to have something that's monostable, the easiest way perhaps to have that is to put some structure in the network. And so what they've done on the right side is to basically separate the neurons into subpopulation, and within each subpopulation, neurons self-excite one another, but across different populations, they tend to inhibit one another. And so if you simulate such a spiking network with some form of internal noise, so what you will get is that you will see that the dynamic is made of an alternation of episodes during which a given combination of clusters are going to dominate the dynamics, meaning they're highly active and they inhibit the other one, okay? And so that's typically what we think about when you think about metastable dynamics, right? And if you want to understand that, a good way would be to say, okay, give me a network structure. I don't want to think about maybe an energy landscape or an effective representation. And based on that structure, that network, can I predict what are those states that are going to arise? And perhaps even more importantly, can I predict the transition rate between those different states? Because that's what's going to dominate the computation, so to speak, at larger time scale. Okay, so I think that's an interesting question, and that's the question I'm gonna follow to introduce this replica-mean-field framework that I mentioned in my title. Okay, so the idea will be, okay, give me a network. Can I get to those states that these networks are going to be in, and can I predict the time scale that will guide the transition from one state to another? Okay, so before I get into the talk properly speaking, I just want to make a forward, is that in that talk, there'll be a few simulations, but I want to be clear that the goal in the method I'm going to present is never to do simulation, right? And I want to basically develop some tools that are going to allow me to make those computations and answer that question in a faster way than simulation. And this is because simulation, of course, have a few drawbacks. One that I just mentioned is that in general, they're costly, and they could be very costly for the kind of question I'm interested in, because you could imagine that there are many timescales. You have to evaluating some timescale, and some may be slow. And so you will have a computational cost that can become very prohibitive due to like the heterogeneity of the timescale you're looking at. Then another limitation of simulation is that, of course, if you're thinking in terms of like something that depends on the network structure has many structural parameters whose finite size can be crucial, and it's going to be especially crucial for inferring transition timescale. So that means we're looking at an object that's very high dimensional, and okay, this is going to be the source of also a lot of complexity. And even if you could address effectively by a very clever algorithm both of those limitations, then you're left with the problem of trying to have a cohesive view of your simulation. And that's very hard to visualize high-dimensional data. And so there can be an argument that the best way to visualize high-dimensional data is to actually exhibit algebraic structure about it, algebraic relation, sorry. And so that's what I'm trying to do. So of course, the problem is that it's almost impossible to do analytics for those kind of problems. But we're still going to try. And in the remaining of the talk, I just want to point out that the key limitation that we're going to try to address is the finite size dependence of the dynamics, meaning we would like to have a good characterization of some feature of the dynamics and be able to relate it to the finite size parameter that are defining the structure of the network, okay? So the structure will be the following. So first, I'm going to introduce the kind of model we're going to use to address those questions. So there's going to be like some spiking networks model and the kind of approximation that have been used in the past to like model them. Then I'm going to introduce the kind of framework that we've done to tackle this question from a slightly different angle. And finally, I'm going to try to address whether or not we can use that framework to answer the original question. That means, can we get at those timescales and can we get at the parametric dependence with the network structure? Okay, so first part, introducing the kind of dynamics we use to think about the model. So these dynamics are fairly general, but I'm going to just introduce them by considering the simplest possible example of such dynamic, which you may think about as a toy model. But the key ingredient that are the source of mathematical complication will be in there already. And so we're not going to talk about metastability right now. We're just going to take very simple toy model where everything is homogeneous, okay? But we want that model to be finite. So here you see this model. There's 5 neurons, and those 5 neurons communicate with one another via a finite parameter mu. So the dynamic of each of the neurons will be characterized by an internal variable. And this internal variable is a counting variable. That's why we call it the counting neuron model. And what does it count? It counts the number of spikes that each neuron within the network has received since the last time it spiked. So it has some finite memory. And this counting variable will serve to determine the rate at which you spike. So the rate will be a linear function of this counting variable. So it's a self-exciting network, it's homogeneous, and it has some form of finite memory. So those models have been formally studied for a fairly long time in math, and they regain a little bit of interest recently. But there are also, like, you know, some more biophysical instantiation that I will dwell upon later on. Okay. So what kind of dynamics does this model produce? So here's maybe a way that is simpler to think about it. So this is a spiking network, right? So I can draw the time axis and look at the spike raster of my 5 neuron population and mark the time at which each neuron spike by a dot. Okay. And so now if I extract a pair within the network and I follow the internal variable, I will have the 2 trajectories. And what's happening on those trajectories? So whenever a neuron that's not in the pair is spiking, everybody increase by 1 unit, right? And when a neuron from the pair spikes, well, the guy that spikes resets to its base value, which is going to be 0 for the counting variable, whereas the other one still goes up. So what should you keep in mind from this little picture? Well, is that the dynamic is fundamentally finite, right? Every time I interact, I will jump up or reset down by a finite amount. So there is a finite interaction component to it. And also the fact that, of course, neurons are interacting, so there's correlation, okay? So there will be correlation in the dynamics. So now, as I say, like, it's a very simple and as simple as you can think of a model that incorporate reset and finite interaction. And its dynamics is going to be fairly stereotypical in the sense that it's also going to relax to a stationary dynamics. And so if you want to understand this state, you'd say, like, okay, maybe what I could do is try to compute this typical state. That means I'm going to compute the probability distribution to find my network at a given state. So it turns out that if you think about it and if you try to solve that problem, also it's very simply stated, it's already impossible. And I'm just going to explain to you why very quickly. So the main reason are due to, like, the 2 key features, which are finite interaction and correlation structure. So if you want to understand why, you have to first realize that with those 2 features, the best thing to look at is not the probability distribution of the state, but something very closely related, that is the probability generating function. And the reason is that it's a more well-behaved, more regular object, but it's just as good as having P, okay? And now if you look at this object G, you realize that based on the dynamics that I just described before, as stationary state, this quantity G shall satisfy a partial differential equation, okay? So if you can solve that, you're good. You've fully characterized your model. So the problem is that it's already impossible to solve. This PD is linear, so that would be good. But the reason why it's unsolvable is because of the occurrence of those terms here, which are non-local terms, okay? Because they relate something that happened in the bulk for Z in the anywhere in my phase space, and it relates it to quantity that are evaluated at the boundary, okay? And the non-locality of those terms has to do entirely with the fact that I'm a finite system for which I'm jumping or resetting by a finite amount, not something that goes to 0. And then because there's this finite interaction, there's also a correlation structure that makes those boundary terms to couple all the variables. So it becomes also highly dimensional. Okay. So it's going to be, even for a model like this, it's hopeless to solve it, and solving it in the sense of having, like, the parametric dependence of the solution over mu, for instance. So what can you do? So if you can't solve the problem, the next best thing you can do is try to solve a different problem that's going to approximate the original one, right? So that's an idea that has a very long history, right? And here I'm just going to present one flavor of it. That means I'm going to just present one way to approximate the original dynamic. And that's going to be a mean field approximation. And in this instance, it's going to be what I call the classical mean field, which I will explain later on what it means. And so what kind of model? So here you have my original model, and I'm going to change it. And the way by which I'm going to change it is I'm just going to scale its size. Okay, so I'm going to make it bigger. And I'm going to hope that making the model bigger is going to become simpler to analyze. But if I make it bigger, then each of my neurons in this larger network is going to be listening to many more of his friends over here. And so that it's still subjected to the same order of magnitude in terms of driving input, I'm going to also scale the strength of the interaction in inverse proportion to the size of the network. Okay, so if I do that, each neuron is now driven by the average input it received from everybody else. And it's going to be the essence of why this is a simpler model to analyze than the original one. And that is because once I average over all my neighbors, my drive becomes deterministic. So that means that my rate effectively will be ramping up until the moment when I spike, and then I do it again. And because now I'm only correlated via this average level of drive, I'm also going to become asymptotically independent. So I destroy the correlation structure, and that makes it entirely solvable. So that's great. And this is just the simplest way you can come up with a mean field model for this. Now the question is it going to be useful for the kind of question we tackle? So if you want to answer that question, you have to look at what's been done in the literature, and like there's an insane amount of work about mean field model about this. And here I'm just citing a few important work about this. So, oh, by the way, I need to mention also that like perhaps a very seminal paper in that field that introduced a kind of mean field limit. The balanced one is from Carl van Vreeswijk that I put here. So if you look at those models, they come in different flavor, but they all have something in common. And that is that they take the large size limit and they assume at the same time some form of scaling of the interaction. And the way by which those models differ primarily is by the adoption of different scalings and also perhaps different structure. So you have the classical limit where it's like in 1/n. You have balanced limit that are typically in 1/√n. And there's also variation of those balanced model, like the large weight limit, which have been recently proposed with the 1/log n scaling. So if you're in the business of trying to infer time scale, it's going to be a problem because it's known in simulation that all those transition time scale very finely depend on the finite nature of the interaction. So that's going to be a problem. And so we'd like to have a way to have an approximate dynamic where there's no scaling of the interaction. And in this way, we hope that we're going to be better able to predict those transition rates, which have to do with the finite size effect, which themselves drive the stochasticity of the network. Okay, so that's for the motivation. Now, so now I'm going to switch to like what method we propose to attack this problem, and we call that Replica-mean-field framework. And just remember that the goal is to preserve the finite size structure of the network, so that mu dependence. So I'm just going to introduce this Replica-mean-field limit on the same toy model. So here's our original counting model with its trajectory, and now we're going to make a replica model of this. So as the name indicates, if I want to make a replica model of this, I'm going to basically make many copies of that network. So I'm going to illustrate that, I'm going to make a 4 replica model. So here's my original model. That's one copy of my network dynamic. And oops, and now I'm going to make 4 copies of those. And of course, if I let them have the same dynamic as the original system in each replica, I've done nothing. So I'm going to have to do something more. And that's going to be the key of our approach. That's the key idea. So in the original dynamic, when my blue guys over here spikes, okay, it's going to send a message, a spike, to the 2 other guys, the green and the red. And it's doing that in the same replica because it has the same dynamic. Now, if I do a replica model of it, now I'm going to like allow this blue guy to talk still with a red and a green guy, but it's allowed to pick that red guy and that green guy, only one, uniformly at random across replica, okay? So when blue spikes, I toss a coin, and basically I pick one replica. So basically, the foundational idea behind our approach is to proceed to a randomization of the interaction while keeping all the finite aspect of the dynamic as is, meaning like I'm always going to speak only to one guy, and I'm going to speak with it with the same strength as in the original network. And so now the mean field limit for such model will be to consider the limit dynamics that are obtained when I take the number of replica going to infinity. So why should you expect that to be a simplification? Well, there was two aspects that conspire against solving those problems. One was the finite aspect. The other one that was closely related was the correlation structure. And so now what's happening is that when you make a replica model, because now the probability that two neurons talk to one another within a short time window become vanishingly small when R goes to infinity, you expect that basically the correlation between every single unit to vanish. And so what you expect to do in this approach is to destroy the correlation structure, but keep or maintain some aspect of the finite size of the interaction. Okay. So if you want to just to like check this point, what you could do is like look at a model like in A, simulate it in like different replica model with different number of replica, and check the cross correlation between each neuron. And so that's what I've done here. So I took a network made of 10 neurons, and I just simulate my finite size replica model for different replicas. So here's the original model, then the 2 replica model, the 5 replica model, the 20 replica model. And you see that it has, for the original model, there's some correlation between the neurons as expected, and it quickly vanishes with the number of replica. So again, I just show you that so that like, you know, it's a numerical illustration of the fact that we achieve asymptotic independence. In practice, I never do those kind of simulation, right? The goal is not to do that, is to actually analyze those limits to find equation that will allow us to characterize the state without ever stimulated. So, okay, so it seems that indeed those limits will destroy the correlation structure. But actually, if you think about those kind of dynamics, it's even simpler than just destroying the correlation structure, because what those models have is that they're an instantiation of what is called the Poisson hypothesis in the field of queuing theory. So what you expect is that when you take this infinite limit size, not only do you have, if you're a neuron, you experience input from other neurons independently, but you actually expect to experience the input as if they were delivered by a Poisson process. Okay, so what I mean is that if you're a red guy, or blue guy, sorry, or whatever, yeah, any guy actually, and you collect the input from all the red guys and you average it over all the replica, it's as if you were receiving this from an independent red guy with one Poisson red, okay? And so what it tells you is that now, if you want to characterize the noisy dynamics that emerge in the Replica-mean-field limit, all you have to do is characterize those rates. Once you have the rates, you have everything, okay? And you can compute all the moment of higher order and so forth. And so before I tell you how to compute those rates, which will be the basis of the computational aspect of the method, let me conclude on the theory part, which is that part, by saying that if you think about it, this kind of approach is not really dependent on anything in the model except for it being a spiking network. So it entirely relies on randomizing the routing of spikes. And you can do that for any network that's spiking, including, for instance, deterministic one, right? So this is really like a key, this approach really relies on the spiking nature of the models. Okay. Okay, so just again, I just show you some simulation, but usually you would never do those simulation. What you want to do is use the mathematical structure of this Replica-mean-field limit to come about some finite set of self-consistent equation that once solved will give you what are the rates of those neurons. And once you have the rates, then you can compute everything about those limits, okay? And so in the next few slides, I'm going to describe what are the methods to get those equations. And I want to be clear that at this stage up there for the theory, it's only relying on things being spiking model. So it's very generic. Now, if you want to be able to solve and to get those equations, like now you have to throw away some generality. It's not going to be possible for every model, of course. And so this is where like you need to make assumption on your model and you need to restrict your attention to specific class of spiking model. Okay. So it turns out that, okay, for the simple term model that I introduced, you can come up with those self-consistent equations that will allow you to compute the rate that which I will call beta, okay? So this is a model, this is the problem we cannot solve. Now, if I look at the replica-mean-field model of this simple homogeneous network, what I would do is I would transform this originally interacting particle system into a collection of 5 independent one for each neuron. I mean, they're all the same. And now it's going to be also, there's going to be independent model for each neuron, but they're going to be also self-consistent. Why? Because, okay, everything is homogeneous. All neurons play an exchangeable role. So that means that my neuron over there is going to have an activity that's going to be driven by 4 times the input beta of all the other neurons. That's the rate of all the other neurons that I can think of as a Poisson process. And this beta has to be such that when I'm driven by those 4 beta, I have to myself output that beta, okay? I'm not going to be Poisson, but I have to have that right beta to be consistent. And so now if I write down the equation that corresponds to that problem, now it's going to be a one-dimensional problem because it's going to be attached to a single neuron. And it's going to be a projection of this equation on one dimension. And now this PDE becomes a simple ODE. It's still going to have some non-local aspect because I have this finite reset size, but all the non-local aspect is going to be captured by this variable beta, which is the rate and which is my unknown. So basically I've reduced my problem via an approximation to a simple ODE that is parameterized by an unknown beta, which I want to find. And so every time you try to reduce your problem to a set of equation in the RMF, the replica-mean-field approach, you will always end up with a problem of that flavor. And what's important to realize about that problem is that as is, it's underdetermined, meaning there's too many solutions that you may expect. So you have to use the fact that there's a physical solution to that problem to pinpoint the solution you want. Okay, so let me be a little bit more precise about it. So if you want to solve that, you have 2 types of unknown, right? You have G and beta. And it's really beta that you care about. And once you have beta, you're going to have G because it's simple OD. So the simplest thing to do is to say, let me assume that I know beta. And let me look at the solution G that I will get. So it's an ODE. So it's not too complicated. And you're going to see that if you look in the details, solutions that come about, assuming that you know your beta, are always going to have something in common, that is, they will have some singularity. So here there's a singularity because the generic form of the solution all have a pole in 0, okay? And that now it's interesting to us, and that's the part where there's a little bit of analysis, is because if my solution G is physical, if it represents the probability distribution of some dynamics, of some stationary state, sorry, it cannot have a singularity. It has to be analytical everywhere, okay? It is due to this form. So that tells you that among all the solutions I can form using this general solution, I can only allow myself to consider those physical ones in the sense that they have to be analytical and they cannot have a pole in 0. And so it turned out that for this simple equation, there's only one of them that's going to be possible. And okay, you can find that. It's not too complicated and it has an integral form. And so now I have a good candidate for a physical solution. And it's going to be indexed by beta because I assume that I knew beta. So now this is really beta that I'm after. So I need to use another property about G that is going to be useful for me. And that property is that if G represents a probability, I shall know its value in 1. G of 1 should be 1. It should not be normalized, just as probability are normalized. And so if I do that, now I'm going to write that G beta 1 is equal to 1. And now that's it. I have an equation that I can put in my computer. And if I can solve it, I have beta. I have my rate. And so basically, that's the essence of solving computationally the replica-mean-field limit. You have to like write down the equation, do some analysis to pinpoint the solution that that are analytical. Once they're analytical, you have to use some condition that traduce the fact that probability are normalized, and then you have a bunch of equations to solve to find the rate. And you do that without ever doing simulation, right? So it turns out that it can be done for problems that are much more generic than the one I consider. So problems that have heterogeneity, problems that have like relaxation to a base level and so forth. But whatever equation you're going to get, they can always be interpreted as input-output relationship. And what I mean by this is that the beta that you see on both sides are not the same. This beta is the beta that's driving your neuron. This beta is the beta at the output of the neuron. So basically what you're doing is really write down the transfer function of each neuron in the replica-mean-field approximation, okay? So that's going to be all for like the math aspect of things. Now the perhaps more interesting question is that, okay, I've shown that to you for very simple dynamics that is not very interesting. Can we do the same kind of approach? Can we adopt it for more realistic model, and in particular for model that may be complex enough to exhibit metastable dynamics? Okay, and so the answer is that actually we can. And so the kind of model we've looked at are those that are referred in the literature as linear-nonlinear cascade models. And we chose the simplest version of those models, so that those one for which now the rate function of each neuron is no longer linear, but it's going to be an exponential function, okay? The reason why you want to at least have a nonlinear function of this form is that basically if you want to develop the kind of method I just introduced to you, and you want to develop it to a relevant network, you need to at least have inhibition and excitation, and to deal with it, you need a nonlinear transfer function, okay? So it's not the nonlinear aspect that's very important, it's the fact that you can deal with inhibition and excitation at the same time. So I'm not going to detail the kind of technique behind this. I can, if I have questions later on. The point is, you can develop the replica-mean-field approach for those systems. And now the question is, okay, so you're able to simulate those rates, but is it of any good for describing the original model, right? Because don't forget that the replica-mean-field limit is an approximation of the original dynamics, and a priori, we don't know if it does a good job at actually capturing the original dynamics, okay? So here I'm just showing that often it does a good job. So I'm just showing you two types of network. So these networks have a connectivity structure that I represent on the right over here. And here on top, this is a network that I think of as feed-forward dominated, because it's basically made of 5 layers of neurons that feed to one another sequentially, okay? And then here I'm considering an homogeneous network, still with a somewhat sparse connection, but densely connected with recurrence, okay? And so what I can do for those models is I can simulate them exactly. So I can spend a very, very long time simulating those networks, and then I can average the activity over a given time window, and I can compute the rate associated with each of my neurons, okay? And then once I've done that, I can take those as ground truth of my original model, and I can compare those rates with the beta, the rates I get from solving my equation in the replica-mean-field limit, and compare those. And so that's what I've done on the left. And so you see that it does a pretty good job. So this is the neuron index, and that's their rates. So in red is the result from a stochastic simulation, and in black is the solution by solving equation. And you see that actually it's pretty good. It's not perfect. I mean, you don't expect it to be perfect. And if you look at it, it's going to be better for this guy on the top than the bottom. And the reason is because when you feed-forward dominated with strong synapses, which is the case here, you put yourself in the best conditions so that the Poisson hypothesis is valid, right? You're like really like driven by people who kick you hard, and there's not that many people who kick you. That's the kind of network connectivity where like the independence hypothesis is going to be very near to be exact, and finite size effects are going to matter. Okay, so that's fine. It seems it does an okay job at capturing the original dynamics, but now what can it do? do with respect to metastability. So, and especially, can we use this computational framework to go about the transition rate? Okay, so at this stage, I'm going to go in like the part 3 of the talk, and I need to say as a forward that it's the question is not going to be settled, but I just want to convey that like this approach already gives you an ender to actually go forward towards solving this problem. Okay, so we looked at the question of inferring a transition rate on the simplest possible example of metastable dynamic, that is a bistable dynamics. And we use a connectivity structure that has been introduced in the context of perceptual rivalry. And so the structure is the following, right? So you have four finite population of neurons. And these have the structure, like they come in two kinds, right? There's excitatory one, yellow and blue, and inhibitory one, red and green. And the network has a symmetry. You can split it in two sides, and basically each side cross-inhibit one another. And so you naturally expect bistability in such network, because if that guy is active, it should silence the other guy. And because there's a symmetry, there's no reason for one guy to win over the other one. So if the interaction is strong enough, you should expect the dynamics of the network to be made of an alternation of dominance period where one side dominates on the other. So if you simulate those networks, so each of those neurons, by the way, is a linear-nonlinear cascade model, right? And if you simulate them, okay, you see that. You see this alternation of episode where like yellow and green is dominating over the other guy and so forth. And you can recapitulate those alternations by looking the average firing rate over the finite population, which is still going to be a fluctuating quantity. And you see that you have those clear alternations. And so if you want to understand that dynamic from a quantitative standpoint, what would it mean? It would mean like, can you find what are those states that I'm visiting? So what is the rate at which I fire when I'm up or down? And how long do I stay up or down when I transition? Okay, so that would be like solving it. And when I say how much, I say in keeping with the network structure. So with the weights, the mu's that are behind those arrows. Okay. And so let's see if we can do anything about this. And we're gonna try if we can do anything about this by using this Replica-mean-field network. So the first step is to try to see what's happening to the Replica-mean-field limit of a metastable system, and in this instance, a bistable one. So the next slide is going to be about this. And so again, I'm making a simulation, but I'm never going to do the simulation other than for the purpose of like illustration, right? so here's the original dynamic of the system. So this guy exactly, and then I'm copy that system, and I randomize the interaction between those two copies. And now I see that I still have alternation between seemingly the same state that I visit because they hover about the same rate values. But what you should see is that the residence time in the up or the down states now increase with the number of replica. Okay, and actually, what you could quantify is that this increase of the residence time with the number of replica is very quick. It's exponential. Okay, and so that's something that we should not be surprised with. It's something that's been noticed for a long time, and that's been observed in almost all mean-field limit, as far as I can tell, is that when you make the system much larger, well, you're gonna still average the effect of a mini neuron. So you're gonna erase the stochasticity, right? The fluctuation becomes a little bit narrower, and that's gonna make your transition time increase exponentially. So basically, you're always gonna turn your system that is metastable into a system that multistable. So you may still have many admissible state, but they're going to be stable. Okay, there's never going to be any transition between any of the states. So that's a problem, obviously. But at least it seems that okay, you can still capture the existence of those states. Okay, so let's check that out. Let's check that it actually works. And the way I'm going to do it is basically I'm going to say, okay, I'm going to look at this network and I'm going to vary the strength of the arrows, and I'm going to check that the prediction that I get from the Replica-mean-field limit in terms of rate matches the rate of firing of my neurons when they're up or down, okay? So I will just have like the rate identity. I won't have the transition at this stage. And so here I'm gonna vary just the excitatory connection from excitatory to inhibitory. And when those are weak, my system is gonna be monostable. When the excitation are strong, my system is gonna become bistable, okay? And so if I simulate the original system, same thing, that's gonna be my hollow point. I see that all of my neurons have somewhat of the same rate, right? And when it goes past a certain value, now there will be alternation between up and down state, okay? And so now if I write down the equation that correspond to those parametric value, and I solve them numerically, I see that just as one might expect, when there's that switch between monostable to bistable regime, well, that corresponds to bifurcation in my solution. I switch from having a single solution to my equation to having two solutions, one corresponding to the up state, the other one to the down state, okay? And so that's good. At least, I mean, I can predict, with some error, what are going to be the possible admissible state, whether up or down. But that is not satisfactory in the sense that I could have the same result decently well with other mean field approximation. So what can I hope to get with the Replica-mean-field limit that I don't get with other method? Well, what I can get is that there's always noise in the Replica-mean-field limit, right? Because whatever system you're going to get at the end is a system that's driven by a Poisson process with a finite rate. So that means there's always a level of stochasticity. And so that means that this rate that I compute is actually the output rate of a neuron that has an internal variable, and this internal variable is fluctuating due to this Poisson bombardment. And so that means that in the Replica-mean-field limit, I'm going to be able to not only estimate the mean of my internal variable, but also its variance and all the moment actually. And so, whoops. So that's what I'm saying here, right? So now I have the mean of the internal variable. I also have the second moment, the third moment. I can do all the moment. And so what it tells me is that, okay, as opposed to other mean field limit, I can now have a sense about what are the fluctuations around any given state. So just again, like to explain this picture, right? So you have the original dynamic of your internal variable x, okay? When you're down, you become negative. When you're up, you're positive. If you use a well-chosen mean field limit, what you can always hope for is to be able to estimate what is the typical value when you're up and the typical value when you're down. So like those two black lines. But now what you get additionally when you have a replica mean field limit is a sense of like how strong are the fluctuation around those bars, okay? And it's because you preserve the stochasticity in the limit, okay? So now that you have that, now you can hope that this will be enough ingredients for you to estimate what you're missing at this stage, which are the transition rate. Okay, and so here's the part where I'm gonna like try to demonstrate that it's enough information to infer the rate on this simple example, and I'm gonna do it in a somewhat non-satisfactory way, but please bear with me. So to do that and to exploit this information in a meaningful way, I have to somewhat guess what is the source of those transitions, what is driving those transitions in the network. And it's not necessarily obvious. And the way to pinpoint what is driving those transitions so that I can get what is the rate of this transition, what I should do is a correlation analysis of my original network. So here I simulate the original network, and I'm going to look at the correlation structure among different population of the network. And if I do it, just looking at a full trajectory with alternation between up and down states, what I'm going to see is this structure, which is not surprising, right? Because when this guy is up, blue and red are up together. When they're down together. So I expect strong correlation between excitation 1 and inhibition 1, and also strong correlation between those guys. And now, because there is cross inhibition, if that guy is up, this guy is down, so they're going to be negatively correlated. Okay, so there's nothing super interesting here. It's just the traduction of the fact that I'm in the bistable regime. And it doesn't tell me anything about what could be the source of those transitions. It just tells me that I'm transitioning. So if I want to do more, if I want to know a little bit more, what I have to do is look at the correlation structure conditioned to one side being up or down. And now if I do that, I realize that, okay, if these guys over there are up, well, that means they're very active and they're driven by their own intrinsic noise because it's a rate model and also the background input that they receive. So by and large, they're going to be independent, but then there's a population group that is going to be strongly correlated, and that's the one that's dominated. Okay, and these are the source of the transition. Why? It's because if you have a transition, that means somehow at some point something unlikely is happening. So that means you will have fluctuations that are larger in magnitude than what you would expect based on averaging. And those fluctuations are likely to emerge in a population that is naturally correlated. Okay, so that's the down population. And so what it tells you is that the rates that dominate the transition have to originate for the population that is down. Okay, so once you realize that, you can say, okay, well, then I can think about those transition rates as the rates that come up from an escape problem. I can use my estimate of standard deviation and position of the states to model now my new effective landscape, which is going to depend on the parameter mu because sigma and x depends on mu. And now I can model the transition rate as an escape time from the well that corresponds to a down state. Okay. And now that I've made this model, I can use all the machinery that's been developed in chemistry, so like Kramer's rate and so forth, to come up with a mathematical expression that will explicitly depend on mu's and compute those transition time. Okay. And if you do that, and we've done it for like this model, you can see that like the expression you get is actually very predictive of the measured transition time. And here I'm just showing how it still work when we vary mu I and mu e, so like both inhibitory and excitatory weight. And it does a pretty good job at predicting those transitions over like almost 2 orders of magnitude. Okay, and so we think that like it's a good indication that like also it's not satisfactory yet because we still have an effective model at some point. But still, it's evidence that the replica-mean-field model, at least for this one, has enough information encoded in itself so that we can predict those transition rates. Okay, so I followed this metastable topic as a theme to introduce replica-mean-field limit. They could have been other themes, but I thought that's one that's as close as possible to the things actually I'm doing right now, to be honest. But I would just want to point out that like there are different ways we can extend this kind of framework. Okay, so the first one is to basically like trying to go away from an effective representation in terms of landscape and really get those rates directly from the replica-mean-field limit. And so we sort of like some ideas about how to do it, and we believe it's going to involve doing some large deviation analysis of this replica-mean-field limit. Basically quantify the exponential rate of decay of the transition rate and like just extrapolate it to the one replica case. Another line of extension is basically to generalize the Poisson hypothesis to a wider class of model than the one I considered here. And also, it would be of interest to actually prove that the Poisson hypothesis holds for like those class of model, okay, which is not easy. And finally, another line of extension that we started looking into is trying to develop or modify this replica-mean-field limit so that instead of completely erasing the correlation structure, you still keep some trace of it, okay? And that is a topic that leads us to actually change the theory aspect of the approach. And I can make some comment if I have a question about this. So these are like the extension I'm like sort of working on right now. Now, before I'm concluding, I just want to say that maybe it was a little bit of math and it's not clear why you should matter. So I just want to finish on two slides that connect it a little bit better to why it may be of interest to a neuroscientist, and at least in relation to metastability. So the first thing I want to point out is that, okay, it's been known for a long time that some neural dynamics have exhibited metastability in the brain. And so there's a well-known example that has to do with the up and down states that are observable during anesthesia or sleep. But there are also like metastable like computation that are involved in like different aspects of neural computations, just like decision making and sensory pathways. And one of the sensory pathways example that I like very much is the following one, and it has to do with how we presumably encode information about taste. So this is a paper about how neuron in the gustatory cortex respond to a different taste. Okay, and this is a paper by Katz. It's kind of like a famous paper in that field. And what this paper is arguing is that, okay, if you look at the population activity of the neuron in response to those different tastes, it seems that for different taste, they visit the same kind of state, right? So like the number here refer to a neural state, right? So state 3, like this neuron is very active, for instance. And it seems that the way by which different tastes are discriminated is not by the identity necessary of the state, but by the time and the sequence with which you visit those states, which tells you that it seems that the brain is able to compute things about its environment by modulating transition rate, which I find very interesting. And that's something that would be very interested in studying a little bit deeper. Okay. So that's pretty much it. So this work results from a series of papers. Most of the thing I talk about in this last one, which is in written in a computational journal. Now, this work has been done in collaboration with François Baccelli, which is now in France. Okay, right here at INRIA. And it's been also done in collaboration with two students. One of which has graduated already, the other one is about to graduate. So Luyan Yu was the one mostly in charge with the computational aspect. So he developed all the techniques to actually like solve the equation that we obtain to compute those rates and did all the simulations. And Michel Davidov is in France and he's working on the theoretical aspect of the approach. So that means he's actually showing, given a certain class of model, whether or not the Poisson hypothesis holds, and he's basically explaining why this randomization of interaction leads to simplification in the dynamic. Okay, and so I want to acknowledge all my findings, and I really thank you for listening to me, and I hope I'm going to have some questions.